start this lecture 37 with a thought process from D. Eisenhower. He was a past president of USA long time back, around 1960s kind of thing, right. He had told every gun that is made, every warship launch, every rocket fired signifies in the final sense a theft from those who hunger, are not fed, and those who are cold and not clothed. When I am talking about this rocket propulsion engine, I must communicate this message, which was similar to mine and told by a USA president who always tried to USA try to have a war and then all sorts of kind of things. So, it is very important for us to understand these things. We should use the technology for the peaceful coexistence, not for a war. So, let us recall what we have learned in the last lecture. I was looking at basically the performance of rocket engine. Of course, before that I had given you a brief introduction to the rockets and its utility and other things, right. And when we discussed the performance of rocket engines, we basically made some assumptions. Those are ideal assumptions, but however, it can be useful for the real analysis as well, because we have seen that it is not very different than that. What is that? That we talked about thrust coefficient, right, and we had derived an expression for thrust coefficient, right. So, we will go on discussing that, and by knowing the thrust coefficient, we can also find out the thrust or vice versa, right. So, if you look at the thrust is basically thrust is PT2, that is nothing but your chamber pressure, into AT. AT is the throat area of the nozzle, right, and keep in mind that I will be using a star, and AT a star for me it is same for the time being, and CT is your nothing but your thrust coefficient. If I know the thrust coefficient and I know the chamber pressure, I know the throat diameter, I can find out thrust, or other way around, right. That means, if I could evaluate the thrust, right, maybe static thrust in a laboratory, and then I know the chamber pressure, I know the throat area, I can get the thrust coefficient experimentally. But what we have derived an expression that is meant for an ideal case, right. This expression CT, which is basically derived for an ideal case, ideal in the sense making ideal assumptions like not losses and other things we have not considered, right. And if you look at this expression which I have shown here, it is basically function of gamma, it is a function of PE exit pressure and also the chamber pressure. We always talk in terms of ratios, right, and other one is your atmospheric pressure and the chamber pressure PT2. Chamber means basically combustion chamber of the rocket engine, right, and a area ratio AE by A star, or I can say AE by AT, right. And keep in mind that when this PE, if it is goes on decreasing, that means PE will be reducing, goes on decreasing, what will happen? This term, right, will be coming closer to the PA, right, it may happen. And what happens to this term for the same chamber pressure? PE is decreasing, this term will be smaller, right. If I take gamma is something 1.2, right, and it is point like 1.2.2, that is basically 5 times into 1.2, this will be coming around 1 by 6. So, the 6 times then this is a very small number, yes or no. That means this thrust is reducing, but this became a bigger quantities, right, because 1 minus this, right, if it is 1 minus that, and it will be thinking that it will be going towards 1 basically 0.99 or something 98 as the PE goes on decreasing. So, maximum thrust can be obtained basically if you look at when the nozzle is fully expanded. This is another way of looking at it, like means if PE is equal to PA, right, this term will be 0, right, and then the thrust coefficient will be basically that is root over 2 by gamma plus 1 gamma power to the gamma plus 1 divided by gamma minus 1 and into 2 gamma square divided by gamma minus 1 in the bracket 1 minus p by pt power to the gamma divided by gamma minus 1, right, and that is the maximum thrust one can think of. So, what you can see that it is only a function of PE and PT2 and gamma, right. Now, if PE is, as I told, PE is goes on decreasing, what will be happening? It will be it will goes on increasing, right, yes or no, this term will be goes on increase, CT naught will go on increasing, right. And what is the effect of gamma then, right? I can vary these parameters, gamma from 1.1 and to 1.4, right. If you look at what is happening, I am plotting over PE by PT2, right, and this PE can be same as that of the PT2, this is the one situation, right, yes or no, it can be worst case, then it will be 1, of course it is we won't be considering. If you consider, then what will happen, this will be 0, that means the thrust coefficient will be 0, right, and we won't get anything out of it. So, that is useless to talk about it. So, therefore, we will consider the PE by PT2 around 0.1 to 0.001. When it is 0.001, when PE is very small as compared to the PT2. If I take the PT2 as 10 megapascal, right, if I take P is something 0.1 megapascal atmospheric pressure, what it would be then 0.001, right, 10 megapascal if you look at 0.01, right, kind of things here, isn't it. If I take PE as 0.1 megapascal, right, and PT2 is 10 megapascal, right, and what will be PE by PT2 will be 0.1 divided by 10, that will be 0.01, yes or no. So, you will be here, and as it is goes on, like it can be 0.01 megapascal, right, then it became 0.001, it will be for the same atmosphere, same chamber pressure, and if I am saying 0.001 megapascal PE, it will be these values. You see that the CF, sorry, this is CT star, right, and CT naught, and it is basically what you call decreases with increase in PE by PT2, right, that is one, right, and it is the gamma effect is very predominant in the whenever the pressure is low, that means exit pressure is very low as compared to the chamber pressure. But as the exit pressure is and the ratio of exit pressure and chamber pressure becomes higher, then gamma effect is negligibly small, all are coming to the almost similar values. Now, you can look at a situation where this PE becomes 0. So, if it is 0, this term will be 0, right. So, we will get a maximum thrust coefficient, and when it is nozzle fully expanded, right, that is the condition we are talking about. No, PE is 0, like you go to the vacuum, right, where PE is equal to PA, right, the vacuum is, right, PE is equal to PA, vacuum condition in the deep sea. I mean, it cannot be 0, but you can assume it is tending towards 0 or something like that. Okay. So, then you will get an expression that is C T max is only function of gamma, nothing else. It is only C T max is a function of gamma. That means we always go for a smaller values of gamma, right, so that you can have a higher C T max kind of thing, right. So, if you look at these, you can interpret and one can, what is the implication of that, that is that you will be designing for a certain pressure ratio, of course, if you are assuming it to be fully expanded, right. And what we will do now, we look at this expression, the generalized expression for the thrust, which is having no what you call condition being placed, in the sense the actual what you call thrust without any simplifications, right, and look at vary this parameter. What are the things will be varying? Will be varying A e by A star, and will be varying P e by P t, and will be varying P a by P t 2, and we are taking gamma as a constant, that is 1.2, right. If you look at this is being plotted C t versus the A e by A star, right. A by A star is your area ratio, that is exit area by the throat area, right. And keep in mind that this is being logarithm, like it is from 1 to 100 kind of things, right. So, what you can note from here, that is, if I take this pressure P t by P e as a 2, right, it is C t is lower than 1, right, okay, and it is goes on decreasing, and of course, and when you go up increasing this, you will find that there is a increase in the, it goes on increasing with the area ratio and reach a peak value here, and then it is decreases, and this area ratio of the nozzle is corresponding to fully expanded nozzle, right. That is the optimum thrust or the maximum thrust you are getting with respect to P is equal to P a. When exit pressure is equal to P a, you will get fully expanded. So, therefore, you will get a maximum. So, if you look at this as you goes on what you call increasing this value, right, P t by 2 by P e, what is the meaning? For a particular chamber pressure, you are going on decreasing P exit pressure or the exit pressure, right, P e or the exit pressure, you will go on decreasing, that is why it is increasing for a particular chamber pressure, right. And you will see that it is similar in nature, that means this is if it is, if I take a, let us say 20, I will take 20 pressure ratio, that is P t 2 by P e. If it is goes on increasing as the area ratio increases and reach a peak value, right, and then it decreases. What it indicates? This peak value is the maximum, the what you call thrust coefficient or thrust one can get, and corresponding to the fully expanded nozzle. Is that clear? That means, in this zone what I will call? I can call this zone is as a over expanded, right. And what about this portion? If I take this portion from here, this portion here onwards, this will be under expanded nozzle, right. Okay. Now, and one is fully expanded, you will get the peak value, both the side the thrust coefficient is decreasing. Now, which one will choose, right? Which one will be more better? Because if I assume that I am, when I am designing, let us say I am talking about, let us say I will take for the 10, like I am having same here and there is another here same, right. I am having same C t value, that is 1.2 if I take these values, right. One is, this side is over expanded, this is under expanded, right. Which one I will choose? Area ratio, and why? It is a very simple logic, I will talk about it, right. Because in this case, if I choose this area ratio, if I choose this under expanded area ratio, so the under expanded case for the same thrust coefficient of 1.2 for the pressure ratio of P E by PT2, right, of 10. So, you will get that area ratio will be around maybe 1.4 kind of, because this is 1.5, right, this is 2, right. So, this will be 1.5, but if I take here it is around 4, that means I am having a bigger nozzle. A E by A star is 4, in one case it is 1.4, right, this will be around 1.4. So, if you look at for the same thrust coefficient I am getting, that means the same thrust level I will be getting for the same chamber pressure, right, is not it, same throat area. Are you getting a point? So, therefore, here I will be using a smaller smaller nozzle, divergent portion will be much smaller. So, my weight will be reduced and my cost will be reduced, right, and payload I can carry more for the same engine, same kind of thrust level. So, therefore, it is advisable to go for a under expanded nozzle than that of the over expanded, right, and from that point of view, but there might be several other points. If I look at the other way around, can I not go beyond this? For example, if I am talking about this, can I not go over like this? Yes or no, right? That is one question I would like to ask. Let us look at what we are observing here. That means if I go on this increasing this PT2 chamber pressure by exit pressure ratio, you will find that it is again increasing and hitting a peak values and then decreasing, and of course, it goes to a whenever it become a maximum value we will get of CT, that is 2.246 when PT2 by PE is equal to infinity. That means the PE is 0, right, exit pressure is 0, or as you told, like it will be occur when it is in a vacuum condition, of course, if it is fully expanded, right, otherwise you can have expansion which is very low, right. So, and if I will that is and you will see that there is a value of 33.3, beyond that there is not really much value you are increasing, because this is increasing and then it is almost this maximum value is almost becoming like that. So, you are not really gaining more, except that you are, as I am going for higher pressure ratios, then my nozzle size, if you look at it, is become 40, 100, kind of things is very big. If I want to even operate at a maximum value, so it is a very big. So, you are not really gaining much beyond the pressure ratio of 33.3, then only people restrict to that, right. So, and if you look at, if I join these peak values, and this line is known as line of the optimum thrust coefficient, that means it is basically maximum thrust coefficient or the thrust coefficient corresponding to the maximum thrust, right. And there is a limit, because if you use this line beyond this, as I told, then there will be also the flow will be separated. Now, why flow will separate? What is the reason? Because if it is over expanded, then what will happen? Let us look at it. I mean, what really will happen? Let us say that this is the what you call a conversion dipole nozzle, and this is the throat region, this is your exit, and the pressure, if you look at, this is your throat where Mach number is occurring, the pressure is changing, decreasing, and it became same as that exit pressure for the nozzle, and of course, the velocity increases as the flow takes expanded in the divergent portion of the nozzle, right. So, then if you assume that you are having a shorter nozzle, right, what is happening? You are having a pressure which is P, right, which is lower than the, if I say this is PA expanded fully, and then it is, that means this is higher, that means there is a some more expansion can take place, right. That means it is under expanded in this case, right. But if you consider that there is another case where it is not P e is not equal to this thing, but rather it is P a, right. That means it is expanded beyond this pressure, and then the P e is basically, right, is a smaller than P a, and if it is smaller, then what will happen? There will be formation of shock, and particularly this shock can be formed, it can be oblique shock, it can be at a when it is very closer to that, there will be what you call the shock will be formed at the exit. But if it is P e is less than P a, and then shock the what you call, or a little bit this thing, then the flow separation will take place. That means if this is occurring, if P e is and P a ratio is less than 0.3, right, kind of things, then naturally the shock, the boundary layer will be separated because the adverse pressure gradient, right. So then when it is separated, then what will happen? Losses will incur, and then one cannot really operate under this condition. So therefore it is being like this line is being considered that where there is the flow is likely to separate, right. Of course it may differ if when you are using various kinds of other nozzle like plug nozzles and then bell nozzles and the conical nozzle, generally conical and bell nozzle is being used, kind of thing. So this you should keep in mind, and therefore whenever you are designing, you will be restricting your operation, and generally preferable that. Let us summarize what we have learned from this, that more desirable to run a rocket engine under expanded condition, that is left to the optimum values what we had seen, rather than the over expanded, because of area penalty, and also it will lead to the flow separations, right, due to the formation of shock, and there will be losses also due to the formation of shock. So therefore, and use a shorter nozzle with reduced weight and size, that I have already emphasized, because and increasing the pressure ratio improves the performance, but improvement diminishes above 33.3, right. We are not really, because we are go on increasing the area ratio, that means weight and size, but we are not getting that much of gain in the thrust coefficient or the thrust level. So therefore that has to be restricted, and large nozzle exit area required at a high pressure ratios, implication for the space application, because we cannot avoid, suppose we want to send some deep space, then naturally I will have to expand, otherwise it will be not nice, it will be like not giving you the desired thrust what you need. So that has to be kept in mind. Now if you look at whatever we have looked at the thrust coefficient, keep in mind that it is talking about the performance of the nozzle, it is not function of the temperature, right, of the combustion chamber, it is a function of what? Pressure, area ratio, gamma, exit pressure, ambient pressure, all those things, right. That means this parameter is talking about only the performance of the nozzle, but we need to understand how well the combustion is taking place. For that we need to define a parameter, right. And let us define another parameter. What we will be using is characteristics velocity, that is basically C star is equal to PT2 A star divided by m dot P, that is the mass flow rate of propellant through the nozzle, right, that is the amount of mass flow rate. And you keep in mind that we always talk about condition known as choked condition, that means the rocket nozzle is all the time or most of the time is choked. So we will be using the term that choked mass flow rate, we know, we have already derived this thing, is m dot is equal to PT2 A star root over RTT2, and of course in the numerator root over gamma, then multiplied by 2 by gamma plus 1 power to the gamma plus 1 divided by 2 gamma minus 1. This we have already derived and discussed several times, right. If I just substitute over here in this equation, here what I will get? You will look at that PT2 by A star will cancel it out, right. So, what you will get is the this C star is basically in terms of gamma, that is 1 over gamma in the bracket gamma plus 1 divided by 2 power to the gamma plus 1 divided by gamma minus 1 Tt2, and Ru is the universal gas constant, m is the molecular weight of the gas which will be expanded in the nozzle, right. And keep in mind that gamma is changing when it is going through the nozzle, but we are assuming it to be constant, okay, but because that value is not really much changing, right. And what it indicates, this characteristics velocity and how it is functionally. If you look at this expression of equation 17, you can see that C star is a function of the chamber temperature, that is Tt2, and the molecular weight of the gas and also the gamma. These are the functions. But what it indicates? It indicates the capability of the combustion chamber that can produce certain pressure, like if you go to the basic definition, chamber pressure per the mass flow rate, for a certain fixed value of mass flow rate of propellant per unit cross sectional area of throat, right. For that, how much pressure it can produce, that it indicates, that is the capability which is indicates. But it is basically independent of, if you look at beauty of this, is independent of the pressure, chamber pressure, although it is definition it is there, but if I look at this expression equation 17, it is independent of pressure, it is dependent on temperature. When you talk about temperature, it is basically how good is combustion is, it, in other words, you can use this parameter as a performance parameter indicating how good the combustion is, right. So, and as I told, C star is a function of basically gamma, Tt2 and molecular weight, and if you look at, if I want to have high C star, whether I want to have high C star or I want to have low C star or the characteristic velocity, what I want. How can I say that now, right? Now, what do we need? We need to have higher ISP, we need to have higher thrust, these are the requirements. So, therefore, we need to look at those things, whether we can relate this C star and thrust coefficient, the characteristic velocity or the thrust coefficient to the thrust or not, or the ISP or not, then only we can talk about, isn't it? But if I want to have C star to be higher, naturally I should have a higher combustion chamber, that is combustion chamber temperature, that is Tt2, and lower molecular weight, because molecular weight, that means lighter propellant I should be using, and of course the gamma even can have a lower values, so that you can have a higher this thing. So, from the combining the definition of thrust coefficient and equation 17, I can have Ct is equal to Pt by P2 A star, then thrust is basically Ct Pt2 A star, right. This from the basic definition, that means thrust is basically thrust coefficient multiplied by chamber pressure, that is Pt2, and A star is the throat area. But if you look at definition of characteristic velocity and substitute this value for Pt2 by A star, we will get basically thrust is equal to m dot p, that is the propellant mass flow rate, C star and Ct. That means if I want to have a higher thrust, then naturally I should have higher thrust coefficient and also the higher characteristics velocity, of course for a particular mass flow rate of propellant. Or if I want to, there is a limitation in these both quantities, so naturally I will have to enhance the mass flow rate of the propellant. So, ISP, if you look at it, is C star by Ct, this is from the basic definition by G. That means if I want to have a higher, what you call ISP, naturally I will have to enhance this and I will have to enhance this, but there is a limitation on thrust coefficient, there will be also limitation of the C star, that is why we can't really go beyond certain ISP, as I had discussed in the last lecture, that is this something in the solid propellant we are having limitation of something 350 of ISP. ISP I mean is the C condition, and that is what you call in second, right, in terms of second. So if you look at the C star and CT, that is as the performance parameter of the combustion chamber, right. C star means it indicates how good the combustion chamber is working in converting the fuel into the certain temperature, right, or how good the combustion is, and the CT is talking about the nozzle performance, right. Now taking this in mind, we can define a combustion efficiency, right. This is basically, you keep in mind, this is eta combustion is equal to C star actual divided by C star ideal. Ideal I can get from this expression, equation 17, right, C star, but then actual how I will get? What I will do? I will have a test rig, right, where I can measure the mass flow rate of the propellant which is passing through it, like this. If you look at the equation 16, that is m dot p, I can measure the chamber pressure, I know the throat area, I can get actual one, right. So if you look at this combustion efficiency is very closer to 1, that means it will be 0.9899, sometimes even 97, like it will get. So therefore it is good enough to talk about even calculate ideal one while designing, okay. But we generally use a value of particular kind of engine, then look at while designing. We have not tested it, we can't really test, so we take this combustion efficiency and use it. Similarly, we can also define a thrust effectiveness, that is epsilon T, that is CT actual divided by CT ideal. CT ideal I can get from the equation 15, and CT actual I can conduct experiment and find it out. While designing, we will be using this epsilon T values, and we know the ideal one, we can estimate the actual one and then carry out the design procedure. So the beauty of this performance parameter, I have already discussed that you can separate it out, and look at it, and then look at this efficiency. This can be used as a design tool for the rocket engines. So let us look at the variation. I did not really discuss there, but let us look at now the characteristics, velocity, how it is varying with temperature, right. So if you look at like it is from the expression, it is very clear, and if I take two gamma values, gamma 1.2 and gamma 1.4, you see this characteristics velocity is increasing with the chamber temperature, and for both the gamma values, and keep in mind that this gamma 1.2, that means low gamma value is having higher characteristics velocity, and a higher temperature the differences is much higher as compared to the low temperature region. That is one thing. And we cannot really go on increasing this, because if I want to have a higher ISP, naturally I will have to go on increasing this characteristics velocity. But if I go beyond something 3500 kind of things, then naturally what will happen, dissociation will occur. Then I cannot really go for that, it will be, you will be reducing temperature. So there is a restriction. Generally people use something 2500 to 3500, or sometimes people say 2700 to 3500 kind of thing zone where they will be operating, right. So now let us summarize what we have learned so far. This characteristic velocity, which is basically thermodynamic performance, and strong pressure ratio effect, as I told you, but rapidly diminishing return about 33.3, that we have learned in the from the thrust coefficient curve, right, versus area ratio, right, for different pressure ratio, and higher Tc, that is basically Tt2. Tc is nothing but Tt2, chamber temperature value, desirable for higher ISP. But problem is that the more the higher the temperature, right, then the heat transfer will be more. That is the one problem. But again, higher the temperature, then dissociation will occur, right. So that means it will be consumed in the process of dissociation, whatever being released. So it will be again inefficient. Therefore, practical limit being used, as I told, something 2750 to 3500. Some people use 2500 to 3500 Kelvin kind of thing. These are all design thumb rule kind of thing one can say, depending on the propellant, because it will be depend, the temperature what you can get will be dependent on the type of propellant you are using, right. So, the low value of molecular weight is desirable, as I mentioned that molecular weight will be lower because favoring particularly the hydrogen based fuels, and therefore you can get higher ISP because characteristic velocity will be higher. Even thrust coefficient, if you look at, one can also get that. So, now we will, I mean, of course, the low values of gamma is desirable, as I already demonstrated through the characteristics velocity plot, right. So, therefore, these are the things you should keep in mind, and we can learn by just carrying out a simple analysis about the performance of the rocket engines. So, I will take an example. In a rocket engine, hot gases at 2500 Kelvin and chamber pressure of 10 megapascal is expanded fully in a CD nozzle with a throat area of 0.15 meter square to the ambient pressure, right, for producing thrust. And we need to determine exit velocity, right, characteristics velocity, ideal thrust coefficient, thrust and specific impulse, and molecular weight you can take 25 kg per kilomole and specific heat ratio gamma 1.25, right, we have taken in this example. So, if you look at assuming flow in the nozzle to be ideal, we can determine these velocities, and keep in mind this is gamma like 2 gamma Ru gamma minus 1 molecular Tt2, and this is Pe by Pt2 power to the gamma divided by gamma minus 1, right. We will substitute because all these things we know, and gamma is 1.25 and the Ru is the universal gas 8314 and molecular weight 25 and temperature is given 2500 and the pressure Pe is 0.1 megapascal, that is same as that of the exit pressure or the ambient pressure, right. We are assuming it to be fully expanded nozzle, that is again and kind of things, and which is given in the problem, that is fully expanded, right. So, and 10 atmosphere is the chamber pressure. So, when you substitute values you will get 2883.4 meter per second, right. Similarly, we can determine characteristics velocities by just substituting values which we have talked about, and all are given. So, you will get 1385.59 meter per second. So, ideal thrust optimum coefficients, and when you substitute these values, because this is fully nozzle expanded, so we can substitute, we will get, we are getting something 2.08 kind of thing, which is quite good, right. And the specific impulse can be determined as C star and Ct, right, this G, and you will get there will be, and you will get 293.85 second you are getting, right, which is solid propellant kind of engines you can think of. Similarly, we can determine the thrust produced by this rocket engine as basically Ct star, Ct and Pt2 and A star. We know all those things, we will substitute, it is something 3.12 mega Newton, it is quite a high power, high thrust engines, right. So, we will with this we will stop over and we will continue.